Today we're going to talk about axiomatic systems, I hope, objectivity, quantum mechanics, and with some questions of theology. Those are the things we're going to try to touch on. I don't know how, you never know how a conversation goes. It has its own organic quality, so we'll see. But to begin with the question of axiomatic systems, and I like this question because it's one of the questions that you asked me the very first time we met, which was a billion years ago. No, it was a long time ago. And that question stayed in my mind, although of course I had no idea what you were talking about. And since then I have a little bit of a better idea what you were talking about. And it has, I realized after that many years how very, very important it is when we raise the question that this table makes nicely for us of foundation or ground. And really the point Descartes makes at the beginning of the Meditations, give me a place to stand. And this Archimedean point, he thinks if I can find this one certainty, I can build the rest of the sciences, all of them, this wonderful tree of knowledge, if I can just find ground. The ground that is unshakable, that will be a fundament that I can count on. Now, that fundament doesn't seem to have anything to do with an axiomatic system, but in fact it does, because we are looking at things that are given, and we base, on the basis of these axioms, everything in any well-ordered system that grows out of them. So we have to take our elements. Euclid's elements are obviously parts of these, the postulates that are taken to be are part of these, and thus the question, how do we, if we're taking Husserl seriously, or we're taking Heidegger seriously, we are looking at really the crisis, which is a crisis in foundations. And it's always a crisis in the ground. It's a crisis for Heidegger, it's ground, for Husserl, it's foundations. And these things may seem to be odd concerns of philosophy, but they're not, because David Hilbert, in 1900, says to all of the mathematicians who gather in Paris to listen to the World Congress, all the mathematicians, he says, these are these problems for you, mathematicians of the world. And he says the problem is the problem of foundations. Why? Because unless mathematics solves these problems, it will not be a science. Now you might think that if anything is a science, certainly Kant thought that. Mathematics is. And yet, in 1900, so many years after Kant, David Hilbert, a wonderfully extraordinary mathematician, is saying, if you're honest, no, mathematics isn't what even Immanuel Kant thinks that it is. It too needs to be put on a firm footing. So, if I ask you that, where do we stand today with axiomatic systems, with the foundation question, with any of Hilbert's issues, and you, I think, have a solution for us, but I still remain somewhat in the dark, as many people do.
Yes, these problems are not uniformly resolved at the moment, but I have ideas, and I will give you, to the best of my ability, how I think about these things. Mathematics, one of the foundations of mathematics is counting, 1, 2, 3, 4. Every one equals every other one. So there is an exchangeability between the individuals. And that raises the question as, is there any individual that remains the same for everybody in all time in history? And you can't say that there is anything that does that. But if it does, mathematics applies to it. And we then normally, in using mathematics in the world, we buy a dozen apples, but some of the apples would be red, some would be green, some would be sweet, some would be sour. They're all apples, and there are 12 apples there. However, some of the buyers may want sweet apples, and some of the others may want cooking apples. And some of them want to draw the apples as part of an artistic work, and others not so. So that when applied, the word one apple has many meanings. And those meanings are, in fact, indeterminate in number. And now we're getting onto the notion of the real notion, or rather, the usable notion of a unit of apple has an infinite number of descriptors that are assumed, because you don't know them all being all the possible descriptors that people might have for the use of apples, for the enjoyment of apples, or for the destruction of apples, or for the something like that, biology of apples. So that once you move from the areas of definition, and mathematics defines all ones to be exchangeable with one another, the real world is not of that kind. Two apples can be quite different for certain reasons.
Yes.
But if we're buying them on the grounds that they are, for the purpose of buying and selling, equal in value, then we can use mathematics. And two apples are twice the cost of one, and so on. For a larger number of apples, there are a larger number of differences, and they'll give you a discount for it, because some of the apples may not be usable in the way that for the reason that you want to buy apples, and so on. Now that's very important as a comment between the pure mathematical, theoretical side of science and the experimental side of science. The experimental side of science deals with existence, reality as the emergence of particulars of what's being talked about in the presence of the speaker. In science, of course, that is laboratory data.
Okay. That's a great set of reflections, and I like the apple example, and I also like the iterative example of the integers. I think that's enormously helpful, and it also seems to point to integers and fingers and things that are ready to hand in a certain sense, or there in a certain sense, so that you have a point of departure. You do have something given, you do have something to begin with, and that's terribly, terribly necessary, one thinks. But then we're back to that question of the givenness of the kinds of things that we take to be given. And it's the givenness of the things that we take to be given, philosophically speaking, not so important when you're building a temple or when you're building a log cabin. Then what's given will be, the apple tree that you cut down to maybe, I don't know how, but I think they make fairly nice logs if you get good ones, the right kind of apple tree. Although then you don't have apples, so people tend not to use them for that reason. But if you are building a log cabin, or if you're building a temple, or if you're building anything with units that are ready-made, that's one thing. Or you're counting apples, that's one thing. But then we're thinking of the idea of numbers, and we're thinking instead of the idea of geometry. And geometry is more challenging in a certain sense than arithmetic, which is the example I noticed you very cleverly used the example of arithmetic, which is of course also what interests Hilbert. And there are big questions about that, and sentences and drawing power, very crucial matters. But with geometry, where the earth is involved from the very beginning of the word itself, we have to do with some other matter than just various givens. And there we're talking about things that almost inevitably take us away from the earth. A point, a line, a plane. And then we're looking at very complicated things when we talk about parallels. So the very famous, and you wrote about this in your book, Space Perception and the Philosophy of Science, the parallel that you draw there is the one which Jesuits have always been occupied with, actually, historically speaking. has to do with the fifth postulate, and this is the real question. And what do we do with parallel lines? And those parallel lines are problematic because of infinity. Infinity is our problem because if we think a point is self-evident, you can even if a grain of sand isn't a point, you get the point. That's a joke, philosopher's joke. It's not a good mathematician's joke, but it's a great philosopher's joke. Or a line. Maybe you think you understand because you understand a line segment, and you continue that. The problem with that is that may make sense in the level of the dimensionality of the line itself. It begins to really run into trouble when you have two of them. One line is actually not difficult to imagine. Why not? It goes on forever, sure. But when you talk about the parallel postulate, then you're running right into vision and its problems with parallels. Because I'm standing on the railroad tracks because I'm lost in the Gobi Desert, and I hope there are railroad tracks so my example works, I don't know. But say I'm lost in the desert in Arizona, and where I know there are railroad tracks, and I find some railroad tracks and I simply decide to follow those to the next train station because I have a good chance, I think, of maybe getting there before I die in the desert. I see ahead of me the tracks converge. So, and of course I also see the horizon and so on because the earth is curved, and all of that's very nice, but what I see is that what's obviously under my feet is parallel, and that I can see nailed into the sand as parallel are the tracks. But what I see ahead of me are that they meet. So it's really almost immediately given that parallel lines always converge, in my experience. And so maybe for that reason it bothers people, but you're still making a claim when you say, and no matter how elegant your proofs are, we just say that these lines can never converge. These parallel lines, parallel, are the main parallel to infinity, or they're not parallel.
Yeah.
Right? I mean, in Euclidean geometry.
Right, Euclidean geometry. Right. The original form of mathematics, which subtended physical science, was Euclidean geometry. Euclidean geometry, like all mathematics, is a human invention that sets up its own postulates and then works independently of observation in the world. Observation in the world, as you pointed out quite correctly, is such that parallel lines going to infinity, like a road, a straight road ahead across a desert, seem to meet in a point, at a finite point, at a finite distance too. Well, that's a problem. That problem in physics can be, has been, or rather, when mediated, or how should I say, when used as an example of physics, will lead a response, and there are two responses. One is that the point of joining in the distance is not relevant to the questions I'm asking, and so the mathematics involved then redefines or defines parallel lines in the typical mathematical way as not meeting ever and always the same distance apart. On the other hand, a kind of mathematics that applies to the world at large, that is a large extension of the world, will have to take into account why our vision does not give us an infinite world, but gives us a finite world. It's not merely railway tracks, but we look up at the sky and we see a dome above with little bright lights in the dome, and the traditions of Europe, the religious traditions of Europe, is that God lived in the space beyond the visible space. In fact, the Greek philosophers held, Aristotle held that space was finite, but beyond a physical space, there were the gods. And the gods were in a different space than the one we lived in. So the discovery in the 19th century that there can be geometries that involve a kind of parallelism that is finite called, these geometries are called curve geometries, and then I got interested in the application of these curve geometries
I have to take this here because, you know,
to human
it's
life
so obvious.
and vision.
See.
Yes, that's right. That's Euclideanly, scientifically, the clouds are in a straight line above, or sort of on a plane above us. But visually, it looks like a dome that goes this way. Vision, classical science.
Excellent.
Of course, classical science also recognizes that the world is round and that therefore the clouds will while they appear to have a flat surface above us, really are part of a curved surface that goes around the world, so a rounded surface. Now, so now we have, and this is about
so this is more accurate. The curved is actually more accurate.
yes, but that curve can be treated as a part of a Euclidean space, which, for the most part, since we localize ourselves at a particular place, this curve is hardly visible and hardly affects a human life. But the other questions arise related to the question of the curvature of the world we live in versus the non-curvature of the Euclidean space of Newtonian and classical physics, because Euclidean geometry is a non-curved space. The first person to introduce the mathematics of curved space into physics was Einstein. He discovered that the cosmology, that is our universe, of which our sun is just one element, one star in many stars, and our star is a star in a galaxy, and there are many galaxies and many stars in any galaxy, and any star can have a satellite like called a planet, and some planets can support life, as our Earth is a planet of the sun, and it supports our life and the life of vegetation and other animals. So when we come to discussing our experience of the Earth we live in, we are face to face with the problem, is the space that we experience Euclidean, or is it non-Euclidean, namely curved? And there is every evidence that, or rather there is much evidence, and it goes back really to Galileo and Kepler, who are concerned about the stars and the planets, and whether God was, or the gods, or the God was above the sphere of the clouds and the planets, Jupiter and Mars and so on, or not, because the public religion and public spirituality looked up to the heavens for God, and the heavens were identified with the space above the stars. Now the telescope, Kepler was the first to apply the telescope to the stars and the planets and showed that the heavens showed no evidence of the existence of God and the angels, which at that time was a major religious problem.
The question that I guess I'm trying to ask about the axiomatic system has to do with Wigner's question. How does, on the unreasonable, nature as he calls it, why does, this is the wonder, this is a miracle, that, as Vico says, as Kant says, we only have knowledge into that which we ourselves make. But then you take a step back and you say, if we made math, and we did, historically there's a history of mathematics, there were many books on it, but if we made math, and the Hungarians wrote most of those books, then Wigner has a question to answer. Why does the math that we made ever work, given that the universe is not something we made, the Earth is not something we made? Why? It's one thing for it to work in the carpenter world. Why would it ever work in a rocket perspective, doing rocket science? Why? How can you shoot Sputnik into the atmosphere and get Sputnik to stay there? Never mind how can you try. The Chinese were trying. They're the ones who gave us the rocket fuel ultimately. But to begin with, you always want to throw things up like a spear. But how do you get it so that your math works, so that you can put something literally into orbit? So much has to come together mathematically for those calculations to actually work. Now those are also the calculations of dropping a bomb on Hiroshima. Those are also the calculations that make the Manhattan Project possible. Learning how to split the atom is light years different from the theory that the atom can be split, which is, a contradiction of what the name means. But why does it work is a really big question.
No, there are two questions there.
Thank you.
In fact, there are more than two.
I thought there were.
Yes. Let me ask let me take the underlying, the question that underlies your fundamental question.
Oh.
Right. The theory that underlies that your fundamental question is how does mathematics work in the sciences?
Yeah.
And Wigner was the first to realize that mathematics, of course, is a science on its own that grows in certain directions as mathematicians explore further dimensions. Wigner saw that Hilbert's space, Hilbert's algebra, of what's called now the Hilbert space, would be the instrument to express what you have just expressed, or rather, the instrument to which the variety of problems that you expressed can be. A Hilbert space is a vector space, mainly. Its basic functions are vectors, meaning that it has a variety of different properties. In classical science, they are the three dimensions of space and the one dimension of time. And there may be a dimension of spin and a few additional ones. So but one is aware that when we experience something in the world to which we give a name, there is a background. And the background has to do with our practices in the world, how we live in the world. An apple can be used in a variety of ways. In fact, an infinite variety of ways, though we can't name an infinite number of uses or values. But what is an apple is the meaning of that is determined by the conversational situation or the business situation or the scientific situation in which an apple is introduced. So let's describe an apple by a vector with a large number of possible properties, possibly significant properties, and that possibility, we don't know whether there's a finite limit to that, or so we say, let's have an infinite number. Let's conceive of an object described by a vector with an infinite number of properties. And now we have a space filled with such vectors. How many vectors are there in that space? Well, as many things as there are in the world of human experience. So we have a geometry of infinite dimensions occupied by vectors with an infinite number of properties. Technically, the phrase is a Hilbert space is a vector geometry with an infinity of spaces. Now one can begin to give names to the properties that we're interested in, and we can go beyond the 3 dimensions of space and 1 dimension of time. And we can add all kinds of other things, like mass, energy, momentum, but spin, and etc., etc., etc. We can't fill in. We are in a community of scientists that are ever discovering new aspects of things, and those new aspects become new variables related to the old variables by equations, and now they're vector equations. And then the question is, how do we, the next question is, of course, how do you apply such a vector space to reality? And we apply it in the laboratory, which has the image of the laboratory, of course, comes from chemistry. Wigner was a chemist. See,
Yes.
He was very well aware of the protocols that one has to use and is obliged to use in a chemical laboratory. Much more than where is the calcium, it's what kind of calcium, and so on and so on. You see?
Very important.
So it was that insight that Wigner, the chemist, had of physics, of quantum physics. And so he defined quantum physics as the physics of the world as seen through the mathematical systems of Hilbert spaces. Now, not everybody knows much about Hilbert spaces, even experimentalists, you see. The mathematics of Hilbert spaces are not simple. It has simple aspects of it. You can learn them easily, but it's deeply involved in algebras and so-called the square root of -1 and infinity. They have to be regularized as terms within the new mathematics. Once they are regularized within the new mathematics, now you have a much larger, let me say, picture of the world, but I'd have to put the picture in inverted commas because it's not really a picture, it's a picture of, it is a representation of the world, a representation where the terms involved are measurable terms in possible human laboratories. Not all the terms will be such that they can be measured at the same way because the use of infinity is connected physically with what's measurable and what's not measurable. Usually it's the dy dx, it is that aspect of calculus which uses dx, dy, dz, dt for the smallest amount that is no longer measurable.